Next slide, Russ. Alrighty, well, thanks for joining us. My name's Itzel Torres with 3C Ren out of our Ventura office. I've started recording this session, so it'll be posted on our on-demand page after the event, and I will also be sending out a post-event email where you'll get the slides and the recording. We have Russ King with us today, and he'll be talking about residential load calculations and duct design for building departments. But before we get going, I just have some housekeeping slides, and if you're new to our network, a little bit more about who 3C Ren is. Next slide. We ask that everybody make sure they are on mute throughout the duration of the course. If you would like to verbally participate, please raise your hand in the participant section and we will call for you to unmute yourself. We also encourage you to participate and ask questions through the chat box, and we'll get to those questions as well. Next slide, please.
It's going through the animation stuff.
Oh,
There we go.
there we go. Just a few words about who we are. We are the Tri-County Regional Energy Network. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura. We work on improving energy efficiency in our region by offering free programs and services for building professionals and households. 3C Ren is funded by ratepayer dollars, which are collected through the Public Goods Charge Fund and our utility bills. And currently we have 3 programs. Next slide, please. Our first one being the Energy Code Connect program, which serves building professionals by offering Title 24 support for everybody from plans examiners and inspectors to architects and contractors. Within the Energy Code Connect program, we offer Energy Code Coach service and over the phone, online, and in the field support for Title 24 related questions for both residential and non-residential projects, and training and support just like the session we're having today. Next slide, please. We also have our building performance training program, which serves building professionals such as architects, engineers, contractors, and real estate professionals by offering technical and soft skills training related to building science principles, high performance buildings, marketing, and communication techniques. Next slide, please. We also have our home energy savings program, which incentivizes contractors and helps residents save money and make their homes healthier with energy efficient upgrades through incentives and rebates. And with that, I'll hand it over to Russ to get us started with today's training. Thank you.
Awesome. Thanks, Itzel. Good morning, everyone. Welcome. Glad to have you here. It's nice to be here myself. Thank you for inviting me. And today's topic is one that's near and dear to my heart. My name is Russ King. I'm a mechanical engineer, a longtime trainer for a lot of the RENs. I started doing residential HVAC design back in 1988. Before there was even software to help you do the load calculations, and this is it's what I do. This is kind of my day-to-day job is teaching people how to do load calculations, trying to get people to do load calculations, and now I'm here teaching building departments how to plan check load calculations. So it comes full circle. As we'll see in a minute, load calculations and duct design for houses has been in the code for a long, long time. In fact, I'm pretty sure California is the only state where the requirement is in actually 3 different codes. It's in the energy code, it's in the green code, and it's in the mechanical code. So if that's not enough for you, I don't know what is. But I can also tell you that historically, it's been very, very poorly enforced. I would say the vast majority of building departments do not ask for load counts, do not ask for duct design or anything like that. The first building department I ever encountered that required mechanical design when you submit for a new house was the city of Las Vegas, of all places, and that was back in the early 90s. They, a lot of Retirement communities were being built in Las Vegas back in the early 90s, and they felt that air conditioning was a health and safety issue for some of these senior citizens, living out in Las Vegas. And so they required a stamped set of plans, engineer stamp on a set of mechanical plans, and we did hundreds of those. It was good times back then. So let's dive into it. The Today's topic is how to plan check it. And I think part of the problem, and maybe you guys can chime in the chat, part of the problem and one of the reasons why building departments haven't been asking for it is because they don't know exactly what to ask for, and if they do get it, they're not quite sure what to do with it. And so hopefully we'll resolve a lot of those issues today. So today's learning objectives is to review the overall compliance process, including prescriptive and performance approaches. And we'll talk about how HVAC specifically fits into that energy code process. We'll understand the code requirements for load calculation and duct designs. What exactly are they asking for, and which codes are asking for it? And then what to do with that stuff. What do you ask for, and what do you do with it? How do you plan check it? And then we'll have some best practices at the very end. So the agenda, pretty much the same process, same flow. We'll talk about the energy code compliance process, the basic HVAC compliance issues, energy code requirements for residential HVAC and duct design, energy code compliance documents, which of all those forms will help you ensure good design of the system. Plan check and field inspection checklists. We've provided some. There's a kind of a basic one and then a super detailed one if you really want to get into it. And then best practices for energy code. And then at the very end, if we have time left over, we'll open the mics and let people ask questions. Feel free to type questions into the chat as we go, okay? All right, so you were emailed the following handouts, or you'll get a link to those shortly. And one of those is called the compliance process flow diagram. By the way, I forgot to mention, this class is a cooperative training between Bay Ren and 3C Ren. It was actually written for Bay Ren. I teach this class up in the Bay Area quite a bit, and so it's great that the Wrens can share classes like this. I think it's good information everybody needs to know. So that's why you'll see the Bay Ren logo everywhere. But in the Bay Ren training, we very often we like to kind of stop and take a big picture view of the energy code and see sort of how stuff falls together. And that's what we'll do with this compliance process flow diagram. And then you should have got a couple of these checklists, okay? And we'll go through these checklists later on. And then you'll get copies of these slides at some point, and then your ICC certification. Ignore the evaluation at the end. That's a Bay Ren thing. All right. So let's talk about the energy code compliance process. And this is kind of a big picture overview that we always like to do in our Bay Ren training to kind of keep us focused on if you get too focused on the trees, you can't see the forest, and vice versa. So, all right. So as you'll probably recall, the energy code consists, first of all, of mandatory measures. Those are things you just always have to do. Okay, they're energy features that have been deemed so cost effective, so important, you just have no choice. You just got to do it. Okay, and that's things like sealing ducts. You have to seal ducts. That's things like certain kind of switches on your outlets or on your light fixtures, and certain kinds of light fixtures, and certain efficiencies of equipment and stuff like that. Always have to be done. But then after that, you have a whole bunch of other energy features to choose from. To choose those features, there's the prescriptive path and the performance path. The prescriptive path, basically they're chosen for you, but it's a lot simpler. So the prescriptive path is the simple but strict path. They tell you what to put in the house, okay, and you have no choice. You got to. The performance path allows trade-offs. So you can create a computer model and you say, well, I don't want to do that, but if I do these two other things, it's kind of the same. And it's the computer model that proves whether or not it's the same. And so there's a lot of trade-offs and things like that. So the bottom line, excuse me, the bottom line is that most new construction, probably 99.999% of new construction, uses the performance path. That's where they hire an energy consultant and they create the computer model and all that good stuff. The prescriptive path is pretty much reserved for alterations, change outs, and changes to an existing building, and smaller additions, okay? Additions can either fall in the prescriptive or performance. I'd say most additions probably also fall in the performance path, okay? And then this is the little handout we talked about. And it's sort of just a one-page visual of the energy code compliance process. Okay, and the thing to really take from this is that energy code compliance process is 3 basic steps. If you really boil it down to its bare essence, it's 3 basic steps, and you can see those steps over here in the far left column. Step 1, figure out what's required. Figure out what you're supposed to do. You use a prescriptive path, a performance path, figure out what you're supposed to do, and you document that on the CF1R. Step 1, CF1R, figure out what you're supposed to do. And then step 2 is do it. Do those things, install them, but document what you've installed. And that's the CF2R form. And then the third step is have somebody check it, make sure it was done correctly, verify it. Some features are verified by a third-party special inspector called a HERS rater, and some features are verified by the building inspector. Okay, the all features have to be documented. All features get a CF2R. Okay, only some features get a CF3R, the third step, the form for this third step, and those are the HERS measures. Okay, if somebody else is doing the verification besides the building department person, okay, they need some documentation. They need some proof that it was tested and then it passed, and that's the CF3R. Okay, so you'll notice the top here, this all happens during plan check. If your project requires a set of plans, okay, it has to go through plan check and review. And if it's the performance approach, there'll be a CF1R perf 01. That's a full-on description of the house or the addition or whatever. And part of the plan check process is making sure that that CF1R matches the plans, the right amount of windows and all that other stuff. And we have a class just for that. It's called the new construction class. But then on the prescriptive approach, they don't use the software. They just look at a table in some sections of the code, and there might be a CF1R depending on the type of project. So there's a CF1R for alterations, for HVAC alterations. There's a CF1R for additions. There's even the CF1R NCB, the very rare, if you're going to do a completely new house, using the prescriptive approach, there's a form for that. Okay, we don't see it too often, but it's out there, and occasionally it gets used. But most new construction follows the performance path, where they use the computer software. Okay, but either way, you still got a set of plans. And in this particular class, we could be talking about a new house, and they need a set of mechanical plans. You could even be talking about a completely new system installed in an existing house. You really should have a set of mechanical plans. It doesn't have to be super detailed. It can be fairly schematic, but in both cases, you need a plan. You need to see a set of plans that shows the type of equipment, the size of the equipment, where the ducts are located, how big the ducts need to be, how the ducts are going to get to where they're supposed to go. That's a real challenge especially in two-story houses, getting ducts from the attic down to the first floor. You need chases. You got to run through crawl spaces. There's going to be plumbing and wiring in the way. There's going to be structural beams in the way. The floor joists may not run the right direction. So you're definitely going to need a set of plans. In new construction, that's fairly common. I've done, many hundreds of those in new construction. But for existing houses, it can be a real challenge because there's usually not a good set of plans available. Okay, but we'll talk more about that. But anyways, the point is that whatever they say they're going to be doing on the CF1R, they need to do that. Okay, then the permit gets issued. Then they start building the house, and then the installers document what they installed. Okay, the CF2R certificate of installation is filled out by the installer, documenting what energy features they installed. And there's a whole bunch of CF2Rs that affect the HVAC system. Okay, all measures, whether it's a HERS measure or a non-HERS measure, they get a CF2R. Okay, and so there's 2 basic categories of energy features: HERS measures and non-HERS measures. And the difference is that the HERS measures are verified by a HERS rater. The non-HERS measures are verified by the building inspector, and they don't have that extra form. If they want to create an extra form, they're more than welcome to, but they probably don't want to. But all the other HERS measures that are verified by the HERS rater get that extra form, the CF3R certificate of verification. Okay, and so that's the process. That's the big picture. Okay, now we're going to talk about HVAC, and in particular HVAC design, which is one aspect of the energy code, so to speak. The problem is that the energy code has historically just assumed that equipment is properly sized. They say, oh, there's this section of the code here that requires that it be properly sized, so we're just going to assume that happens. And it it rarely does. Okay. It's a big problem. I see it every day. I see the ramifications of poorly designed systems, and all this other work that we're doing about sealing the ducts and making sure the airflow is good and all this other stuff. It just flies out the window if the entire system is not properly designed. So that's why this is a big issue to me personally. All right, so basic HVAC compliance issues. Let's talk about some of the things that the energy code addresses related to HVAC. So HVAC, heating, ventilation, air conditioning. HVAC covers a wide range of topics when we talk about energy use. Okay, we've got our air conditioner running in the summer, we got our heater running in the winter. What affects how much energy those two systems generate? Okay, so we're not going to worry too much about ventilation. Ventilation is pretty well regulated. It's covered by ASHRAE 62.2. It's a HERS measure, so it gets tested. Okay, so we're going to kind of set that aside and focus on heating and cooling energy use. So what impacts how much energy a heater, whether it's a gas furnace or a heat pump or an air conditioner, uses? What affects that? Okay, the first thing is its efficiency. Is it a 12 SEER, 16 SEER, 14 SEER, 18 SEER? What's the AFUE? What's the efficiency? The efficiency of a unit is how well it does its job based on how much energy it consumes. Okay, so a gas furnace consumes gas and it gives off heat. How well it does that is its efficiency. And you could have 80 SEER, or sorry, AFU, you can have 80% efficient furnaces. That's not very good. You could have 96% furnaces. That's really good. Okay, heat pumps are rated differently, but they bring in electricity and they give you heat. Okay, they're actually super efficient. Okay, so its efficiency of the equipment itself is a big impact, and the energy code regulates that. Okay, the energy code talks a lot about efficiency. You can get extra credit for modeling high efficiency. It becomes a HERS verified measure and all this other stuff. So we're pretty good at doing that. We've been doing that for quite a while. The next thing is its size. Okay, how big is it? How big is it? You got, for air conditioners, you can have a 1.5 ton, you can have a 2 ton, 3 ton, 5 ton piece of equipment. Okay, clearly a 2 ton piece of equipment is going to use a lot less energy than a 5 ton piece of equipment. But what determines the size of the unit that goes on the house? Well, that's something called the house's loads, the load calculation. That's what sizes equipment. And the energy code has always just assumed that it's properly sized for the equipment. And that's a big assumption. Okay. Chapter 4 of the residential compliance manual has a really good discussion about all the HVAC and all the different components. Okay. Even things like duct location, duct leakage, that's all part of the HVAC system. That all comes into play. Okay. And then lastly, how much does it run? And then how you got a piece of equipment on a house, how much that system runs is regulated by the weather. Okay. And how well the homeowners operate. Let's say the homeowners are using the house correctly, they're not leaving all the doors and windows open. How often a piece of equipment runs is going to be determined by the outdoor conditions. Okay. So efficiency of the equipment, the size of the equipment, and the weather. Those are the three things that really affect energy use. Okay. Now we've done very well enforcing proper efficiency, and we have no control over the weather. The weather's the weather. All right. It's this one here in the middle, the size of the equipment. We've really neglected to do a good job on that. Okay. So let's talk a little bit more about efficiency. I kind of got ahead of my sides. The energy code regulates equipment efficiencies. SEER, EAR, HSPF, AFUE, we're all familiar with those, and those are easy to check. You just look at the make and model number, find it, the AHRI certificate or whatever, and look, that's not too difficult. It's gotten more difficult than it used to be, but it's not that bad. And then system performance, there's actually some tests that HERS raters do to make sure that things are working correctly. Okay, there's an airflow test, 350 CFM per ton. There's a fan watt draw test, certain watts per CFM. There's a refrigerant charge test to make sure it's properly charged. That's all great. I'm a huge fan of airflow and fan watt draw. That helps to make sure the ducts are properly sized, but it doesn't help to determine where the air is going. All it does is make sure that they can handle all the air. We're like the only state that requires that. And when I tell people, I deal with contractors all over the country, and when I tell them that in California you put in a new system, you have to test the airflow, they're like, holy, well, that's crazy. How I wish they would do that here, you know. So it's pretty amazing. And then fan watt draw, refrigerant charge. But then as far as the ducts themselves go, the R value of the ducts, that's a big impact. Where the ducts are located, you're starting to see more houses, more architects trying to bring the ducts inside conditioned space. That has a big impact. And then of course duct leakage. We've been testing ducts since the 80s. And hopefully we've got that down pretty good. All right. But again, all of this is we've been doing this for a while, and it's fairly well enforced, especially in new construction. Okay. These are all, regardless of the type of equipment, um, and most of these are HERS verified measures. So we even have specially trained inspectors going out to test this stuff. Okay. So this is all pretty good. We've been doing this well for a while. Here's where it kind of falls down: the size of the equipment. Who determines how big a piece of equipment should be on a house? Well, the equipment capacity of, so let's talk about the equipment itself. How much heating and cooling does a piece of equipment give us? That's called the capacity. The equipment capacity depends on the climate. Okay. A 3-ton air conditioner in San Luis Obispo is going to give you a lot more cooling than that exact same 3-ton air conditioner in Palm Springs. Okay. Because the outdoor temperature is so different in Palm Springs. It has to work harder to deliver that capacity. So when we start talking about capacity of equipment, it's very important to understand there's something called design capacity. Design capacity is how much heating cooling it'll give you at design conditions at the location where the house is being built. Okay. And it varies by climate. Then of course, the efficiency of the building envelope. How efficient is the envelope? How much heat is it letting in that we have to extract with the air conditioner, or how much heat is it letting escape that we have to replace with the heater? So those are all very important things. So we got to look at the capacity of the equipment and what the house needs. The energy code assumes that equipment is properly sized. There is no place in the energy code that actually checks that except one place, and that is for heat pump sizing. Okay, if you model a heat pump in the performance approach, it'll ask you to check the heating capacity at certain conditions, and that's so that it's not undersized and runs too much on the electric resistance strips. Okay, but other than that, for air conditioners, for furnaces, there's nothing that really says, there's no check that says, is this piece of equipment properly sized? Okay. It's all completely relies on the other part of the code that says you must do load calculations and you must follow manual JS&D. Okay. Or equal, which I'll tell you right now, there's really nothing or equal at this point, that nothing that's easy to use. Okay. So when you see in the code and it says manual JS or D or equal, the only other thing that's equal is just like basic math. It's like doing it on a notepad or something like that. So manual JS and D are the only really software driven thing that's easy to use. But it's not to say someone couldn't come up with something right away. Okay. All right. So the energy code assumes the equipment is properly sized. That what happens if it's not? Let's talk about that. This is not always the case, which is why enforcement of this part of the code is so important. Even the most efficient equipment, the very best piece of equipment in the tightest sealed duct system you could possibly imagine in a super insulated house, will not do a good job maintaining comfort if it's not properly sized. Okay. Now, what do we mean by not properly sized? Well, there's two particular problems. One is too small and one is too big. Guess which one's more common? Too big is way more common. Guess which one causes more comfort complaints? too big causes more comfort complaints. So you can be too small, that's obvious, but you can also be too big. And that's something that even veteran HVAC contractors don't realize. Okay. So size versus load versus efficiency. So many contractors do not do accurate load calculations, and then they oversize the equipment to be safe. It's just human nature. You do a load calc and you're not really sure, or you're just kind of ballparking. You're going, I'm going to round up a size just to be safe, quote unquote safe. All right. Many people mistakenly believe that oversized equipment will use less energy because it runs less, and they think, oh, it's like putting a bigger engine in your car. You can just go faster and it performs better. It's not the case. Okay, that is not the case. Oversized equipment wastes energy and is more prone to comfort problems. I have data logger graphs that show what happens when an equipment is oversized. It short cycles and it never runs long enough to let the air mix properly. So oversized equipment negates all the efforts we've done, to check the efficiency, to test the ducts, to check the airflow, all that other stuff we've been doing. If you oversize the equipment, you've just blown all that stuff out of the water. Okay. So, and why is it so bad? Well, oversized equipment short cycles. That means it runs for a really short period of time. It blasts cold air, or if it's an air conditioner, or it blasts hot air if it's a heater, and then it shuts off. And then it blasts hot air and then it shuts off. And it blasts hot air if it shuts off. That's called short cycling. That does three bad things. It causes comfort problems. Okay. The house never circulates enough to be even temperatures. So you get stratification. The old hot upstairs, cold downstairs is usually most likely caused by oversized equipment. So comfort problems, you're using more energy, and the equipment's going to fail sooner because it's going on and off so often. Okay. So those three bad things are caused by oversized equipment. What happens if you undersize equipment? If you undersize equipment, it's not going to keep up on the most extreme days, but the rest of the time it's going to be just fine and it's going to save a lot of energy. So it's actually not as bad to undersize equipment. If you undersize equipment, it'll just be the worst thing that's going to happen is just going to be a few degrees warmer than what they want, or a few degrees colder than what they want. Okay. But compare that to the problems with oversizing equipment, where you're going to have temperature fluctuations in the house. You're going to be using more energy, and your equipment's going to fail sooner. Okay. Which is the worst of those two evils? And to me, oversizing is the worst of two evils. Okay. Instead of looking for excuses to oversize equipment, we really should be looking for excuses to make the equipment smaller, and not necessarily undersize it, but get it down to where it really should be. Okay. So what does the energy code say about all this? Well, and first of all, why is it important? Why do we even care? All right. Well, it is actually a health and safety code. Okay. Adequate heating and cooling during extreme temperatures. The California Mechanical Code says you must provide a furnace that will heat the house to a certain temperature, 5 degrees off, 5 feet off the floor, whatever it is. And so, if you have senior citizens living in a house and you have a cold, very, very cold spell, you need a place for them to stay warm. Okay. In Las Vegas, they consider air conditioning a health and safety issue. If you're having a 115-degree day, you need a place people can go to stay cool. All right. So health and safety, energy efficiency. All right. Oversized equipment will run at suboptimal performance and it'll waste energy. Undersized ducts reduce airflow, which reduces efficiency and capacity. That's another problem with air conditioners and heat pumps, is they rely very heavily on good overall airflow. Air blowing across that coil that's heating and cooling the air. If you start choking off that air that's blowing across there, it reduces capacity, the ability to heat and cool, and it reduces efficiency. So it's kind of a double whammy. All right. And then comfort. There's no code that says a house has to be comfortable. Okay. It's sort of a side benefit, but isn't it the thing that homeowners are most likely to complain about? If they buy a brand new house and it's not heating or cooling properly, are they going to complain? Yes, they are going to complain. They may not complain about high energy bills. They may not complain about, a little bit of noise coming from the HVAC system. They may not complain about, the color or whatever. Oh yeah, they probably will. But comfort is one of the most common complaints from homeowners, okay? And comfort is always going to suffer when you don't do a good design, okay? All right, so equipment sizing. Load calculations are critical. Load calculations are critical to properly size heating and cooling equipment. Undersizing will cause the house not to heat or cool well on extreme days, which is a very small period of the time, okay? Oversizing can cause excess stratification, uneven temperature distribution, plus higher energy use and short equipment life, okay? And it's not going to work most of the time. It's going to be a problem. Undersized equipment is only going to be a problem on those very few extreme days. Oversized equipment is going to be a problem the rest of the time, okay? Undersized equipment will work fine on milder days. Oversized equipment will perform worse on milder days. Some of the oversizing problems can be mitigated by variable capacity equipment, and you're starting to see more and more of that, okay? If equipment has the ability to throttle down on milder days, that's great. It can act like a smaller piece of equipment. But the problem is contractors still oversize it. And there's a great saying, an oversized an oversized variable speed air conditioner is the world's most expensive single speed because it's only going to run on the low speed, except in very, very rare cases. And so you still, even if you're using variable speed equipment, you should still size it to the maximum capacity to the load. What some people do is they oversize it and they say, well, it'll throttle down. And then what happens is it never throttles up. It always runs on the low speed, and they've just wasted all that money. Okay. Duct sizing. Duct sizing is almost as important as equipment sizing. Okay. Target room airflows need to be determined by room loads. How do you know where to put the air in a room? Most contractors will just wing it. They'll say, oh, it's a bedroom, it gets a 6. Oh, it's a family room, it gets an 8. Oh, it's a bathroom, it gets a 4. And they just size by room versus duct size. That's a horrible way to do it, okay? What you need to do is know each room's load. I've seen tiny rooms need a lot more air than much larger rooms because they have a lot of glass. Maybe they have a sliding glass door facing west, and the other big room doesn't. It has a small window facing north. Okay. So you need to know the load of each room to know how much air needs to go to each room. And then you size the ducts for that air going to each room. Okay. So that's what we call air balance. That's getting the right amount of air. But the other thing is the overall, the total duct system needs to be able to handle all of the air. Okay. And just a ballpark number to think is 400 CFM per ton. The minimum is 350. That's what HERS raters will test for to make sure it's at least 350. They really should be designing to 400 or better. Okay. So if you've got a 3-ton system, you should be moving 1200 CFM. The question is, are there enough ducts in the entire system to handle 1200 CFM? Excuse me, I got the hiccups. You don't know unless you do a good design. Okay. General undersizing of all ducts, especially return ducts. That's usually the bottleneck, is the return, will reduce system fan flow. And that fan flow, again, reduces the capacity and efficiency. So it's super important. Okay. All right, load calcs and duct design are rarely done correctly. Historically, the most common method of equipment sizing was rule of thumb and trial and error. This almost always leads to oversized equipment and undersized ducts, okay? I'm sure you guys have heard the 500 square feet per ton. Maybe not so much out on the coast where a lot of you are, but you come inland a little bit and you'll hear people say, oh, 500 square feet per ton. You know, that's not a load calculation, okay? I teach an HVAC design class, and I have a house that I can make it go from a 3.5 ton, sorry, from a 2-ton to a 4-ton, 2.5 ton to a 4-ton, just by rotating it 90 degrees. I didn't change the square footage. Okay. What it does is it changes the glass orientation. If anything, you should be doing tons per square foot of glass, not tons per square foot of floor area or square foot per tons. Okay. So that's not a load calculation. You have to do a good load calculation. Manual J is the industry standard for load calculations. California Mechanical Code 601.2 requires manual D or equal to size residential ducts. Okay. So if you're doing a new house and it's got ducts in it, the mechanical code says you must use manual D to size those ducts. But then it doesn't mention manual J or S, load calculations and equipment selection. But if you go into the normative section of manual D, it does say in order to properly use manual D, you must use manual J and manual S. So it essentially does require a full design for any new system where you're putting in all the new ducts and stuff like that. Okay. And then this is interesting at the very, very back. Appendix A of the California Mechanical Code, you'll see this little thing. It's got the ACA logo on it. And it's a little plan review form. How about that? A little plan review form that tells you what to do. We've sort of taken this. You can use. You're more than welcome to use this, but we've taken and sort of expanded on it. And this has actually expanded. ACA has a much more involved one or more detailed one than this too. But you're more than welcome to use this or the one that we're or one of the two that we're providing you. All right. So there it is. This is in the mechanical code. All right. It's also in the energy code. The California Energy Code requires manual J or equal for all new residential systems, whether in a new house or an existing house. That's a mandatory measure. Okay. And then the green code specifically calls out manual J, S, and D. It says heat loss and gain shall be done according to manual J. Duct system shall be sized according to manual D. Equipment shall be selected according to manual S. Okay, so the mechanical code, the energy code, and the green code all basically require these things. This has been in the code since 2013. Here we are 11 years later, and it's still not very well enforced. Okay, and probably because it just building departments just haven't been trained on it. They don't not sure what to ask for. So here we are. Here we are. All right. HVAC contractors should be doing it anyways. Okay. I deal with a lot of HVAC contractors every single day. I started off asking them nicely, please do a load calculation. I've started bossing them around, say, hey, really need to do a load calculation. I've tried begging, and now I've resorted to shaming them for not doing load calculations. We have a sticker somewhere. We have a sticker and it says, do you even load calc, bro? that we hand out at trade shows and stuff. But what I tell them is, if you're a carpenter, if you're a woodworker, what's the saying? Measure twice, cut once, right? Be absolutely sure before you cut. Okay. I'm not a professional carpenter or a woodworker. I'm a hobbyist. So I tend to measure once, and I usually end up having to cut twice. Okay. That's just me. But if you're not measuring at all, if you're just guessing, can you even call yourself a professional? If you're just guessing at what size equipment needs to go in this house, how can you possibly call yourself a professional? And a lot of them will say, oh, well, that's what was in there before. So you're assuming that the person before you did a good job sizing equipment, which is probably not the case. Okay. And you're just going to put in the same bad equipment. All right. That's not how it should be done. I'm a proponent. Now, if it's an emergency situation and someone's furnace breaks down and they need a new furnace right away, I'm not saying you need a load count for that. But if someone is considering upgrading their equipment and saying, look, my equipment works okay. I'm thinking about having it replaced because I want it more efficient, or maybe I'm going from gas to heat pump, you absolutely positively should do a load calculation in that situation. You have the opportunity to do a good job at that point. Plus, by doing a load calculation, they can start identifying places in the house that might be easy to improve, like adding ceiling insulation or sealing the house to actually reduce the loads of the house and then properly size the equipment to that more efficient house. Okay. It just makes sense. All right. So so contractors should be doing this anyways, and it's really a shame. I mean, some of them have actually resorted to writing articles in major publications making excuses for why they don't have to do load calculations, and I think that's ridiculous. Okay, now I will tell you that 10 years ago, to do a load calculation on a house could take you several hours, especially in an existing house where you didn't have a set of plans and you had to go out to the house and measure it. But here's the deal, technology in the last couple years, technology has changed dramatically that makes this really easy to do. Okay. And there's no more excuses. There really isn't. Here's the actual energy code itself, the language. Okay, 150.0H. There it is, manual J, and then it says or equal. The ASHRAE Handbook of Fundamentals, that's the math. Manual J is actually based on the math from the ASHRAE Handbook of Fundamentals. Then the SMACNA Residential Comfort Installation Standards Manual, that is not a load calculation manual. I'm not even sure why it's here, to be honest. It's a duct installation standard, how you install your ducts, how you install your equipment. And guess what it says for load calculations? It refers to manual J. Okay. So if you ever see anyone say, yeah, I do ASHRAE load calcs, okay, chances are they don't. All right. Manual J is a industry standard load calculation based on ASHRAE, okay, and there's several computer programs that use it. The only place you might see is if in some of the energy code compliance software, they use the ASHRAE, the more pure ASHRAE formulas to do the load calculation. That's the only place you're really going to see an ASHRAE load calc done, is some of the energy modeling software. Okay. All right, so there's the energy code. Now here's another important thing. Not only does the energy code tell you that you have to use manual J, it tells you what design temperatures you have to use. For heating, it's 68 inside. For cooling, it's 75 inside. So the indoor temperatures, the indoor conditions are set 68 winter, 75 summer. Okay. I have no idea where the 68 came from. That snuck into the code at some point. It flew under the radar, and I'm not sure where it came from. For many, many years, it was 70. And I even got corrected one time. I was doing it at 70, and they go, no, it's 68 now. I go, what are you talking about? So it's 68 now. So it's actually a lower temperature. And then the outdoor temperatures that you're supposed to use, okay, come from a table. Joint Appendix JA2. There's a list of 500 and something cities. Find the city that you're in and use the temperature for that city. Okay, that's what Manual J says. HVAC contractors monkey with those temperatures all the time. They'll look at a temperature like Sacramento and they'll say 99. The outdoor design temperature is 99 in Sacramento. Oh my God, it gets way hotter than that. It hit 105 last summer, and then they'll change it to 103 or something like that. Don't allow that. That will result in oversized equipment. They don't need to do that. Manual J, I hate to say this, Manual J has sort of a built safety factor. Manual J is a safe load calculation, so they don't need to add all this cushions. Okay, so that's set. Looks like we got a question here. Rebecca is asking, how does the passive house software compare to the Manual J load calculations? I'm not exactly familiar with the passive house software. If it has a load calculations built into it, you'll want to check and see, are those ASHRAE based, or are they actually doing a heating and cooling load calculation so that you can size your equipment? That's different than an energy model. An energy model will tell you how much energy a house will use over a year. A load calculation is a point in time. It's when it's this temperature inside and this temperature outside, and it calculates heat loss so you can size your heater. And in the summer, it calculates heat gain at a certain conditions so that you can size your uh, air conditioner. Okay. If you feel free to send me, actually, I forgot. I'm going to type in my email because it's not on the slides anywhere. Russ@codedenergy.com. And if you guys have any questions about what we talk about today, feel free to email me. And Rebecca, if you want to send me more information about the passive house software, I'd be happy to look into it. I've never used it. I'm not familiar with it. All right. So what are these ACA? ACA, you hear ACA all the time. ACA, ACCA, Air Conditioning Contractors of America. It's the largest trade association in the United States for HVAC contractors. They publish these ANSI approved manuals. ANSI approval is a big deal. ANSI means it's gone through a very rigorous development process and public review process, and sort of peer review and public review process. So they go through a lot of trouble to get these published, which is why they're very regularly adopted in the code. They're widely recognized as the industry standard for residential HVAC design. They're not the only recognized standard, but pretty much they're it. Okay, they're adopted into most codes. They're in the Uniform Mechanical Code, which is what the California Mechanical Code comes from. There are 3 basic manuals. There's a whole bunch of manuals, but the 3 main ones are Manual J, which is for load calculations, Manual S, which is equipment selection. How do you pick a piece of equipment to meet those loads? And then Manual D is duct design. Okay, those are the 3. There's a 4th one you might see once in a while, Manual T for terminal selection. That's all about sizing registers and stuff like that. But I'll tell you from my experience, if you do a good Manual J, and you properly size the equipment, don't oversize the equipment, and you do a decent duct design, it doesn't matter what kind of registers you put in the house. It really doesn't. I mean, it helps. It'll make a small difference. But when I teach the class, I tell them, a good design will forgive a lot of sins, and and you don't have to worry about exactly the kind of register, exactly where you put it and stuff like that. I'm not saying that stuff's not important. I'm just saying it becomes much less important if you do a good Manual J, a Manual S, and Manual D. Okay. Why my slide button stopped working? There we go. So software. You have to have software to do a good load calc. I started doing Manual J's before there was software, and all there was worksheets, and you filled out these worksheets, and it was horrible. It was tedious. You could do a block load, which is a load on an entire house, without too much trouble. But to do room by room load calculations, oh my God, you had to figure out how much wall, floor, ceiling, windows each individual room had, and you had to add those all up, and it was brutal. Okay. And so now there's lots of software. So if you go to the ACCO website and you search for software, you'll see the old dog Wrightsoft has been around forever. Elite's been around forever. I'm not too familiar with AdTech. Florida Solar Energy, they have a software called Energy Gauge, which is actually used inside of another software program. Yeah, it's a quick model with energy gauge loads. Okay, I don't know anything about Carmel Soft or Avenir. And then there's CoolCalc. CoolCalc is the online one. CoolCalc is approved for Manual J. If you put in the right information in the CoolCalc, it'll give you a correct answer. The problem is the input is so simplified. You have to be really, really careful with it. If you see CoolCalc loads, check the inputs really carefully, because CoolCalc has a tendency to convince contractors, oh, you just guess, just guess, you're fine. and it doesn't work so well. So be very careful with those. Here's the big 3 that do Manual J, Manual S, and Manual D. All these other ones, these all do Manual J. But if you want duct design and equipment selection, these are the 3 main ones. Wrightsoft has been around forever. I've used Wrightsoft since the day it came out, and until a few years ago. Elite is very similar to Wrightsoft. And then in full disclosure, Quick Model with Energy Gauge Loads is my software. My son and I developed Quick Model with Energy Gauge Loads. So I just want to throw that out there, full disclosure, but I'm not telling you which software to use. I'm just telling you pick a software. Whichever software you use, learn to use it, because we get a lot of people who purchase software and they try to learn the software, but they're not familiar with Manual JS and D. So they're really learning 2 things at the same time. They're learning design Manual JS and D, plus they're learning software, and that can be very difficult, but they need to do that. We recommend that they take a Manual JS and D class that's software agnostic, and they learn the basic process first, and then start taking classes on whichever software they use. Okay, but these are the 3 main ones. These the approved. So got a question here. Are these the approved ACCO software for plan review? These are all Manual J certified software. Yes, and they're adequate for plan review. Yes, they are. But they also do duct design. That's what I was getting at. So these all do Manual J. If all you want is a load calculation, all of these will do load calculations. But if you want a full design with duct sizing and everything, these are the 3 that you want. Okay. All right, so let's talk about the design process really quick, just so you guys, if you're going to start checking other people's work, okay, you need a basic understanding of what the design process is all about. So, definitions. We'll talk about some basic definitions. We'll talk about the basic steps. There's 4 steps. Then we're going to cover heat pumps, and heat pumps are hot topic, no pun intended, um, that have some special things you need to be careful about. One of the things with heat pumps is they're very susceptible to bad design. All the bad things you hear about heat pumps, oh, they blow cold air, they hiss and scream in the winter, and they have the defrost cycles and everything gets cold. They blow air on people. All of those problems you hear about heat pumps, those are design problems. Those are not equipment problems. If you do a good heat pump design, you won't have those problems. Okay, so we'll talk a little bit about heat pumps, and then we'll look at the, not an example project, but the checklists. Okay, so real basic. The first thing, most basic thing you need to understand is that your heating and cooling system, your heater is replacing heat that's escaping, and your air conditioner is removing heat that's coming into your house. So there's two things. There's what the house needs, the load, and what the equipment gives you, the capacity. And in order to maintain a constant temperature, your equipment needs to have a capacity equal to the load of the house, okay, but not oversized and not undersized. So determining what the house needs is your first step, and then picking a piece of equipment that will meet that is the next step. Capacity is the heating or cooling equipment output. It's what the equipment gives you. Think of that as the supply. Okay, we need something, and that's the supply. The load of the house is the demand. It's what the house needs. So that's the demand, that's the need. The equipment is the supply. So in order to properly determine your supply, you have to first determine the demand. And here's another little tidbit. Before you increase your supply, always consider reducing demand. Always consider reducing demand before considering increasing supply. Okay. If you think if your equipment is undersized, okay, chances are it's not. It's very rare that equipment is actually undersized. But instead of thinking about getting a bigger heater, think about reducing the load of the house first. Okay. So supply and demand. Good equipment sizing is the ability to match the supply to the demand. Okay. But here's the deal. Very few contractors are actually calculating the demand. They don't know. They're looking at the size of the house and going, oh, 500 square feet per ton. Okay. They're guessing. They're guessing. If you don't do a load calculation, they're guessing. Okay. And chances are they're going to guess high, and they're going to have all those oversizing problems. Okay. So undersized equipment is when the load of the house, what the house needs, is greater than the capacity of the equipment. Okay. And if that happens, that's usually it's not gonna be huge. Okay. It's usually a little bit undersized. So it's not gonna heat on those really, really cold days. It'll drift. Okay. Instead of being 68, they're gonna set it at 70 or 72. Instead of being 70 or 72, it might drift down to 68. That's not the end of the world. Okay. We're not talking that the pipes are gonna freeze. Okay. So that's one, that's undersizing. And then oversizing is when the capacity of the equipment is way bigger than the load of the house. And I'm talking way bigger. I'm talking twice. I've seen it twice where the air conditioner was twice as big as it needed to be. Okay. It's more common than you think. Manual S sets out some guidelines. The first thing that Manual S requires is that you do a load calculation so that you know what you're shooting for, and then you size your equipment based on a percent of that load. Okay. For air conditioning, you're actually allowed, Manual S allows you to be 10% undersized. It allows you to be your capacity of your equipment can be 10% less than your load. Manual S allows that because it realizes that Manual J is safe and that equipment is still going to work the vast majority of the time. Okay. But then it says do not oversize by more than 30% if you have variable speed equipment, 20% for dual speed, and 15% for single speed. So it says don't oversize by more than 15%. Okay. For single speed equipment. So, but like I said, I've seen equipment that's 30, 40, 50, 100% bigger than it needed to be. And that's very common. So design conditions are the outdoor temperatures. Okay. They're not the very worst temperatures on record. They're what's called the 99 percentile. which means the outdoor conditions are only worse than those temperatures 1% of the time. Okay. I got a comment in here. ICC Energy Code requires capacity to meet the latent load. Latent load, yes, that is now. Latent load is not a big deal in California. We're considered a hot, dry climate. Latent load is the ability to remove moisture from the air. And 99.999% of the time, if you size your air conditioner to meet the sensible capacity, it's going to have enough latent capacity to meet the very small latent load that we have in California. Okay. If you were in Mississippi or Florida or Louisiana or something like that, sometimes equipment is sized for the latent load, not the sensible load. So the sensible is what changes the temperature. The latent is what removes heating capacity. So yes, you are absolutely correct. It's just not that big of a deal in California. There are a couple places in California, San Diego. I think maybe you guys on the coast might have some substantial latent loads, but your outdoor temperatures are so mild that it's usually not a big deal. Okay. Let's see. The difference between the indoor design temperature and the outdoor design temperature is called the delta T. Okay. Summer and winter. There's a delta T for summer and a delta T for winter. Okay. That's what drives heat transfer. Okay. All right. Let's see. The process. So basic steps in designing a typical ducted central system. Okay. Here's the basic process. Step 1, collect information about the house. Step 2, perform the room by room load calculations. Step 3, select the equipment to meet those loads. Step 4, design the ducts. Okay. So that's the basic steps. Sometimes for new construction, collecting information about the house is not a big deal. Okay. You can, you've got all the plans in front of you. You've got the Title 24 calcs. It's all there. For existing homes, it can be a little bit more of a challenge to collect information about the house. You've got to go out to the house. You got to measure the house. You have to do an audit on the house for insulation and stuff like that. Okay. We'll talk about that. So let's talk about heat pumps really quick. So what is a heat pump? Why is it so darn popular right now? Heat pumps are all electric, as we know. But here's the thing, rather than creating heat, like a gas furnace creates heat by burning gas, an electric resistance heater creates heat by running electricity through electric resistance heater that get hot. Okay. Heat pumps don't create heat. They cheat. They steal heat. They borrow heat from the air that's already there. These BTUs already exist. Everything has BTUs in it. Even a block of ice has BTUs in it. How do you get the BTUs out of a block of ice? You take another block of ice that's even colder and you put them in contact and the heat will go to the colder block of ice. Okay. So BTUs move heat. They move heat. And so it takes less electricity to move heat than it does to create heat. So here you see, we take these little flying kitchen matches represent BTUs, 5 units of electricity, okay, that equal 5 BTUs. We run that through an electric resistance heater, which are really efficient. They're pretty darn close to 100% efficient. And you get 5 units of heat. 5 units of electricity, you get 5 units of heat. That's about as efficient as you can get, okay? Not really, okay? Because electricity or heat pumps, they cheat. They take 2 units of energy and they use that energy to steal heat from the air around it. So they take 2 units of energy and they steal 5 units from the air and you get 5 units out, but you've only spent 2 units of energy, sometimes less. Okay. Heat pumps can be 300% efficient. All right. And so that's why they're so efficient. That's why we like them so much. Okay. So there's a lot of programs to get people to switch to heat pumps. Okay. Let's see. They've improved the controls dramatically over the last few years. There's what's called cold climate heat pumps that'll work down to negative temperatures. I don't think you guys are going to see too many negative temperatures on the coast. Okay. The coast, a ideal climate for heat pumps. The Bay Area is an ideal climate for heat pumps. Most of California, except the very, very high altitudes, Truckee, Mammoth, Tahoe, but heat pumps are working fine up there. People are installing heat pumps in there and they're working great. Okay, so there is no outdoor temperature limitation for heat pumps. Don't let anyone convince you that. If you do a good design on a house, heat pumps will work great. Okay, I know people in Minnesota that have heat pumps on their house. I know people in Maine that have heat pumps on their house. Okay, and they're perfectly happy with them. They were well designed and they're working fine. Heat pump technology has been used in other countries for much longer than the United States. Okay, but the problem with them is if you don't design them correctly, they won't behave very well. Okay. And that's what makes homeowners angry. I gave a big presentation in Orlando a few weeks ago. I was on a big panel and the title of the talk was how to avoid the great heat pump revolution of 2027, or sorry, the great heat pump revolt of 2027. Then, the theory is that we're going to put in all these heat pumps and not do good designs. The homeowners are going to be really upset and they're going to tear out their heat pumps. They're going to throw them out in the street and demand their gas furnaces back. Okay, we called that the great heat pump revolt of 2027. And so the talk was how to avoid that. And the bottom line was do a good design. Do a good design and the heat pump will work great. Okay, so heat pumps come in a variety of configurations. Typical split ducted systems have been around for years. The first house my wife and I bought back in 1990 had a heat pump in it. It was a brand new house and it had a heat pump in it. Okay, and it worked great. It worked fine. We had no complaints at all. It was the older style, the big condenser with the big air handler, and it worked fine. Heat pumps instead of having a gas furnace, they have a fan coil unit. Okay, no gas lines, no flue vents, no combustion air needed. They're much safer. That's my big thing. Being an HVAC designer, I always was a little nervous about putting a furnace in somebody's house, to be perfectly honest with you. You're piping an explosive gas into somebody's house. When you use that gas, it turns into a poisonous gas. Okay. If you open up a furnace, take the front cover off your furnace if you have a furnace and look at all the wires and tubes and switches and everything. Those are all safety features. Open up a fan coil unit, all you basically see is a switch and a fan and some wires, and that's it. Okay. That should be a big clue anyway. So I'm a huge proponent of heat pumps purely for the safety aspect. Okay. Then we have their ductless mini splits. That's the hot new thing these days is the mini splits. And one of the cool things about them is they come in much smaller sizes. Prior to mini splits, the smallest size heat pump you could get was 1.5 tons. That's way too big for an ADU. Okay. ADUs can get by with like 3/4 of a ton. And that's half of what a 1.5 ton is. Okay. So one of the nice things about mini splits is they're much smaller and they're more appropriate to well-designed smaller dwelling units, which are very common right now. But you can also have multi-head. You can have one condenser that controls several heads. Okay. And then you can have ductless and ducted. Okay. I'm personally a fan of ducted because they get better distribution. Okay. But then you have to make sure those ducts are inside conditioned space and all this other stuff. There's advantages and disadvantages. Ductless to me is like the old wall furnace. Okay. They heat and cool the room that they're in really well. But is that heating and cooling getting to the adjacent rooms that don't have a head in them? And so people say, well, we'll just put a head in every room. Well, then it's way oversized. Okay. So you do have to be careful with those. They're not the magic wand that a lot of people think they are. They still need good design. Here's a ductless system. Okay. So you have these little soffit mounted air handlers. Okay. You can have multi-head or single head ductless and ducted. You can mix and match ducted and ductless too. They're very cool. They're very, very cool, but they're not, like I said, they're more complicated to design than people think. So make sure that the type of heat pump that was required on the CF1R matches what was installed. Make sure the load and the duct calculations are submitted and checked. Note if a special new credit called a VCHP credit, this is very common for ADUs. You'll see the VCHP credit. This triggers some extra HERS tests, but let the HERS rater deal with that. Just make sure you check all the HERS raters forms. Make sure they all get signed. Use the HERS registry and all that good stuff. Okay. Make sure all the CF2R MEC and CF3R MEC forms get registered. In other words, they have a green dot in the HERS registry. If you guys aren't familiar with using the HERS registry, that is a class you really, really should take. So call 3C Ren and ask them for the HERS registry class, because the HERS registry makes it really easy, or much easier, I should say, to make sure all these forms are getting filled out. All right, let's talk about the forms. How are we doing on time? Doing pretty good. Pretty good. We might even have some time at the end to ask questions. Let's see. ICC got another comment here, Roger. Oh, I missed a couple questions. Charles, is there a prohibition on oversizing equipment anywhere in the code? I get RISE-off reports that specify 2%. Yes. Well, the simple fact that the code says you must follow Manual S says you can't oversize equipment. Manual S says 15 for single speed, 20 or 25 for dual speed, and 30% for variable speed equipment. So if the code says you must follow Manual S and Manual S says you can't oversize, then there you go. That's, to me, that's the code saying you can't oversize. Let's see. Roger, ICC prevents exceeding the capacity by 115%. Yeah, that comes from Manual S, and that's actually only for single speed equipment. I think if you read a little deeper, it'll say for variable speed equipment, you can go up to 130%. Okay, that all comes from Manual S. Yeah, yeah. Oh, let's see here. Let me catch back up here. Okay, energy code compliance documents. Here we go. CF1Rs, CF2Rs, CF3Rs. Remember, CF1R, figure out what the house needs. It's documented on the CF1R. CF2R is documenting the actual equipment that was installed. The CF3R is the HERS raters forms. Okay, so using the prescriptive approach. So this is going to be existing homes and smaller additions, the prescriptive approach. So this will be a good example of this would be a house that's switching from a gas furnace to heat pumps, and they're getting all new equipment and all new ductwork. Okay, so they'll fill out a CF1R Alta O2. Okay, if they're adding on to a house, maybe they're converting the garage into a couple bedrooms, and they want to upgrade the HVAC system to handle this new load. Chances are they probably could get by with the existing system. It's probably oversized, but anyways, they do all the calcs and everything, and so they're gonna run new ducts, they're gonna put in new equipment. Okay, so CF1R will have all that information on it. It'll say, you know, what exactly are they installing, what exactly are they doing, and then the CF2R, the installing contractor, takes the make, model, and serial number of the equipment that's installed, and they put it on the CF2R form. Okay, there is a checkbox or is a little statement on the CF2R that says, what load calculation method are you using? Okay, uh, look at that. Then the MEC 20 is where they document duct leakage testing. The MEC 22 is the fan efficacy test for new duct systems. The MEC 23 is the airflow test. Let me just say something about the airflow test. I mentioned 350 CFM per ton. 350 CFM per ton. That is the absolute minimum that's allowed in California for a new duct system. Think of that as a D minus. 350 CFM per ton is a D minus because 349 fails. 1 CFM less than 350 fails. That's a D minus. Okay. A C score to me would be like 400 CFM per ton. Okay. You really should be up around 400 CFM per ton. But if you don't properly size the ducts, they won't handle 400 CFM per ton. Then you'll be lucky to get 350 and then you'll barely pass. Okay, that happens all the time if you don't do a good manual D duct design. Okay, refrigerant charge verification, all climate zones, all AC systems in climate zones 2 and 8 through 15. Okay, a lot of the coastal climate zones don't require refrigerant charge verification. Only the hot ones do. You get over the hill into you know, Paso Robles and stuff, I'm pretty sure you will. That's a hot climate zone. Return duct sizing alternative to MEC 22. I'm not a big fan of that. So instead of measuring fan wet draw and airflow, they can put in gigantic return ducts and assume to pass a test. I'm not a huge fan of that, but it is allowed. Okay. And then the CF3Rs, that's all the HERS forms. All of these CF2Rs that end in an H, there'll be a CF3R that the HERS rater fills out. Okay. Make sure all these get filled out in addition to requesting the manual JS&D calculations. Okay. This is stuff you should be doing already. All right. All this, collecting all these forms, making sure they get filled out. We're just saying keep doing that, but also it's very important to do the load calculation side of it. Let's see. There's a HERS, Charles. There is a HERS rater in the valley whose duct leakage was 0.15 every time. Now it's 0.10 every time. HERS rating is overwhelmingly fraudulent. I wouldn't go that far saying overwhelmingly fraudulent. There are a lot of anecdotal cases of HERS raters doing less than optimal inspections, but there's actually a reason for that, Charles, because a lot of times HERS rater, I'm not saying this is exactly what happened, but there's a reason that that does happen, is that the HERS rater goes out there, hooks up their equipment, and it fails, and the contractors start sealing stuff up, and they keep sealing and sealing and sealing and sealing and sealing until it gets right down to the passing thing. That's why you'll see a lot of them where they're right at the passing because they sealed it until they passed. We see that all the time. I used to work for CalCerts, and so I saw all that data. So, but I will tell you that for every one anecdote you hear about a HERS rater not doing a good job, there's 10 others out there doing great work. Okay, I really discourage you from disparaging the entire industry based on a few examples. Well, based on a lot of examples, but in the grand scheme of things, it's a small sample. Okay, prescriptive approach. So this would be mostly new construction and larger additions. Same stuff, but there's a lot more forms because there's a lot more extra credits you can take that are documented on forms. Duct leakage testing, duct location verification. Here's the same stuff: fan watt efficacy, airflow, blah blah blah. Rated equipment verification. This was that heat pump capacity. This is the one HERS measure, or the one measure period, that verifies equipment size, and that's for heat pumps if you use the performance approach. Okay. And then the CF3Rs. Okay. So this is all basically, we're just saying, here's all the forms that affect all the efficiency. Keep doing that. That's all still important to do all that stuff. All right. But now this is all based on the assumption that the equipment is properly sized. Now let's talk about how we make sure the equipment is properly sized. Okay. So other documents. These are things that are not typically required with building departments. If your building department requires this already, you're way ahead of the game. Okay. So plans, HVAC plans. What are we talking about? We're talking about a floor plan of the house showing the ducts, the duct location, the furnace location, the duct sizes, maybe even the airflows at each register. That would be nice too. These don't have to be super detailed. Most of my career, a big chunk of my career, was running mechanical engineering departments where we drew mechanical plans in CAD. They were beautiful. They were gorgeous. We had CAD people just draw. That's all they did was draw plans that I sketched up. Okay. They were gorgeous. You do not need to be that detailed. Okay. They can be schematic. All you need to know is where's the air handler located? How is the duct getting from there to the register? And what are the sizes of ducts along the way? And then the calculations that support all that. Okay. So the plans can be schematic. And all we're talking about now is heating and cooling. Okay. The plans that we used to submit for tract homes and stuff like that, was doing design in Las Vegas and all that. I mean, they had to show dryer vents, they had to show all the venting, they had to show the calculations for combustion air, all that. I'm not talking about this stuff. This is purely just comfort. Okay. Manual JS&D, heating and cooling. Okay. If you want if you're asking for all that other stuff too, it can be on that plan, but it could also be on the floor plans as well. Need to show duct sizes. Okay. If it's round ducts, they'll show the diameter. If it's rectangular ducts, they'll show 2 dimensions, height and width. Okay. And it needs to show the layout. You know, is it a trunk going to splitting out to 2 branches, or is it what we call a home run, which is just a duct going all the way to the register from the plenum? Those are common too. Okay. What kind of fittings and junction boxes are they using? It should be a reasonable representation of the rooms on the floor plan. Doesn't have to be perfect. Some of you have seen the right saw printout. Very, very crude, but it's good enough. Okay. Calculations. Confirm the approved method. How did they do their load calculations? Look for the powered by ACA-J logo on the software. That was that little circle with the ACA logo. Okay. Energy Pro compliance does use an ASHRAE based load, but that's a block load. That is not a room by room load. You can do a room by room load with Energy Pro, but that's really tedious. The load summary pages, there should be printouts showing a summary of the loads. It'll show all the design temperatures, maybe even some little pie charts and stuff like that. That's just a summary, but you also need details. You need to know what wall assembly did they assume? What kind of window did they assume? Those all in the details, okay? And then the equipment specifications, make, model numbers, AHRI tested capacities, and then the design capacities. What is the capacity of that equipment at the design conditions? Not nominal, but at the design conditions. Very important. Okay. Use the registry to track all forms. Okay, this slide should actually be a couple up in front. We're talking about all the CF1R, CF2R, CF3Rs. Use the project status report to make sure all that's going in there. I wish there was a checkbox here for load calcs and duct design, but there's not. Okay, it's not a HERS measure. Maybe it should be. Maybe we should propose that. All right, plan check and field inspection checklist. Actually, there's a special credit you can take. Anyways, I'm getting sidetracked. There is a special credit you can take um, that allows special energy credit for doing a certain kind of design and having all your ducts buried and short runs and stuff like that. That actually does trigger HERS verification of the duct design. We'll have to think about that. All right, plan check and field inspection checklist. So all those things I just mentioned, we have a checklist for that. One of your handouts. It's so if I guess you already sent these to them. If not, we'll get those to you ASAP. But here's a checklist. This is similar to the one I showed you before. That's actually Appendix A of the mechanical code. It's very similar to that one. But then there's this much more detailed one that's actually recommended if you do if you're doing subdivisions, if you're doing tract homes, and they're going to build lots and lots of houses, you need to do a much more thorough plan check of their designs to make sure they're building all these houses correctly. And there's this checklist. And if you look really closely, there's something called the ANSI ResNet ACA Standard 310. That's a very rigorous, detailed it's sort of residential HVAC commissioning is what it is, but it's also checking everything up through the design process as well. And so we've developed a checklist based on that standard. Okay. So there's this basic checklist and then there's a super detailed checklist, whichever one you want to use is fine. So here's the basic checklist, load calc and duct design checklist. So it has code references. I guess we should add the mechanical code in here, 602.1. And then here's plan check. So ask for a duct layout. Okay, can be schematic unless required otherwise. Okay, should reasonably show duct layout, duct sizes, target airflows at each register. Ask for room by room load calculations, manual J. Room by room loads, not block loads. You cannot design duct with a block load. You have to have room by room loads. So there's gonna be a summary. There's something called a short J form that just summarizes everything. But then you also want the details that shows all surface areas and the associated loads for each room. Okay. And then your indoor design temperatures. These are set by Title 24. Your indoor heating design temperature should be 68. Your cooling should be 75. That's set by Title 24, the Energy Code. The outdoor design temperatures, they come from reference appendix JA2. And it's for heating, it's a winter median of extremes. You got to look that up. For cooling, it's the 1% dry bulb. You look that up and you write that in here. Don't allow arbitrarily raising due to microclimates. They do it all the time. Okay. 1% coincident wet bulb. This is rarely an issue in California. We're pretty much a dry climate, but it does go into the load calculations. Building features for new homes, they should match the CF1R. So you're comparing the manual J calculations to the CF1R to make sure they match. And then the CF1R has to match the plans. So what conditioned floor area did they use? What window areas did they use? The U factor, solar heat gain coefficients, make sure those are similar between the Title 24 calcs. Infiltration, what leakage did they assume in the load calcs? For new construction, don't assume anything higher than 5 ACH 50. That's another place where contractors will use to pump up the load calcs is they'll say the house is leakier than it really is. Okay. Existing homes, watch for excessively high values. There's no reason to model a house to be this leaky, 10 ACH 50. If a house is that leaky, the house is broken. And you don't want to size equipment to a broken house. They should seal that house up, get the loads down to a reasonable number, okay? Before, I mean, don't just slap a huge air conditioning system on a really leaky house. Seal the house first. That's what I was talking about earlier. Address the demand before addressing the supply. Duct R value, location, leakage. Check those against the Title 24 calcs. Selection, manual S. The CF2R MECO 1 is going to show what equipment was installed in that house. Use that as a basis for checking. I mean, that's that for field inspection. Sorry, we're still in plan check right now. Manual S report, if available, the make and model, the AHRI certificates for actual equipment efficiencies. The AHRI, if you look at condenser coil, air handler, the efficiencies change depending on that. And the only way to know for sure was with an AHRI printout. We've been doing that for a while. You should be fairly used to that. Design capacities, the cooling outdoor temperature, CFM indoor, these all affect the design capacity. So make sure they calculate the capacity based on these design numbers. For heating gas furnaces, just use the output, that's fine. But for heat pumps, they need to give you the 17-degree and 47-degree design temperatures or capacity, sorry. Allowed oversizing, undersizing, see the manual S report. So that's the 15% oversizing, 115%, the 100, I can't remember if it's 120 or 25, whatever it is. I think it's 120. And then 130, they're allowed to be 30% oversized if it's variable speed. And then field inspection, make sure the installed features match the CF1R, which should have matched the manual J. Installed equipment should match the CF1R, which should match the manual S. And the installed duct should reasonably match the duct design layout. The main thing is duct sizing, and they can always go up a size. Don't stress if they put in a bigger duct than was called for on the plans, but if they go down a size, that's bad. Okay, and I wouldn't worry too much about, the plans show the duct running this way, but they installed it going this way. I wouldn't worry too much about that. Okay, it's mainly the size and the basic layout is the important stuff. The size of the ducts and the basic layout is important. Okay, let's see, I got some more questions I missed here. What about insulation on ductwork and on the air handler? That's all spelled out. That's something we've been dealing with forever. That's spelled out in the Title 24 calculations. If it's a change out, R8 is the minimum in most climate zones. I think there might be a couple climate zones that still allow R6, but it's a prescriptive measure. So that's an energy code feature that's been around forever, but it is something that it'll be checked elsewhere, and it has been checked pretty well over the years. But it is a very important number that goes into the load calculations. So you might want to make sure that whatever they installed is the same number that they used in the load calculations. Charles, we had an install that went legal, tested the HERS rater 0.47. The HERS rater retested it. Is in agreement with me on the yes. Okay. All right. Best practices. Make sure all required forms get registered by using the project status report in the HERS registries. Okay. That's standard practice. We've been doing that for a long time. If you guys are not familiar with using the HERS registry, request that class. Okay. There's a very good class. It's taught by Bayrin, and I think 3C Ren also does it. How to use the HERS registries. Those are amazing tools to help you check all the forms and stuff. Require and check load calculations and duct sizing for all new systems and system upgrades. Okay. Make sure the assumptions used in Manual J and Manual S reports are consistent with energy code requirements. Wow, there's just a big bang outside. Make sure assumptions used in Manual J and Manual S reports are consistent with what is installed in the field. Okay. And the final word. Most contractors who have learned how to do good design appreciate the benefits of it. Okay. There's a lot of really good contractors out there, and I don't want to disparage the entire industry, but they are few and far between. Okay. Most of them have believed that it takes way too long to do a load calculation, and nobody's paying them to do it, and everyone wants a free bid and blah, blah, blah. And they've gotten away from doing it, and they feel that they've gotten by without load calculations. That is not true. Okay. Homeowners benefit the most from good design by having a comfortable house that is also cheaper to operate. If homeowners knew how important good design is, they would insist on it. Okay. Enforcement and education are critical to improving a major flaw in the HVAC industry. So hopefully by requiring more of this, there's going to be resistance, and there's going to be a lot of, yeah, okay, I guess it's okay, and that's fine. But we need to get in the habit. We need to change the industry and get them used to submitting it, and then we'll improve over time. Okay, very important. Okay, that is all I got. Itzel, if you wanted to kind of wrap it up. Oh, let me see if there's one last comment. Angela. Thank you, Angela. I appreciate that. All right,
Awesome.
Itzel.
Thank you so much, Russ. Just some closing remarks. If you have any questions regarding AIA or ICC learning units, feel free to email me. I'll drop that just briefly in the chat, my email. We do have those learning units available. Coming up in your inbox, you'll be receiving slides, recording from us. So you'll have that if you want to reference to anything Russ said earlier in the training, and just some upcoming trainings that we have scheduled for the end of February and the first and second week of March. I'll also make sure to drop the link to our calendar in our chat very briefly. Next slide.
There we go.
And just a reminder, we do have our energy code coaches that are local experts who can help answer any Title 24 questions for you. There's an online form where you could submit your either project or question, or just directly call them to the number on this page. I'll make sure to link that as well. And with that, I'll hand it back to Russ for any final questions you may have. Thank you.
Yeah, feel free to ask questions. We've got about 3 minutes left. Javier's got his hand up. Can you unmute him, or can he unmute himself? Oh, go ahead, Javier. I think we can hear you.
Yes, so I had a question on the kitchen exhaust fans.
Okay.
There's a default that shows anywhere from 100 to 350 CFM with the zone of less than 3. For the people that want to install maybe a bigger unit, is there a way to do in that and able to comply with something, maybe a bigger exhaust fan?
As far as the zones is going to be the issue, I think. You can always put in a bigger exhaust fan in terms of CFM airflow, but it's usually the zones that's going to get you. You just have to. I think the problem now is there's just a very limited number of manufacturers who make very quiet, large kitchen exhaust hoods. I think that's a problem, right? The only other thing is if you can document why you need a much larger one, and maybe get an exemption from the building department. The whole reason they have a zone requirement is because they don't think people will run them if they're too loud. But if you say, oh no, we need it, and I know they'll run it, so why have the limitation of the zone ratings? That would be my only suggestion. But I've heard other people say that there's just not a lot of manufacturers out there that make quiet, large kitchen exhaust fans. So yeah.
Okay, thank you.
You're welcome. Itzel, did you have the handouts for this, or do I need? I think I forgot to send to you.
I don't. So if you could
Okay.
send them to me, I'll make sure to link them on our follow-up email.
Okay, cool. All right. I don't see any more questions. Well, thanks, everyone.
Alrighty. Have a great day. Bye.
Bye-bye.